Hey guys, welcome to today's video, which is on double replacement reactions. You may remember from first year chem that we often called these the partner swap reaction. So if you think of two couples that go to the prom and then somewhere during the evening they decide to switch partners for a dance. Okay, so that's what this cartoon is showing. Specifically, in a double replacement reaction, we're going to recognize these because the two reactant compounds are ionic compounds and they are in solution. Okay, let's look at an example. Here I've got potassium chloride in solution reacting with sodium bromide in solution. So the first thing you're going to do is predict products based on that swapping of the anions. So we're going to say that the potassium will form a compound with bromide and the sodium with the chloride. So that's the prediction of the products based on that swap the anions. Okay, now let's look at what's happening on a particle level. We have potassium chloride aqueous. So that notation is telling us that this compound in solution is actually potassium cations separated from the chloride anions. Remember, that's what soluble ionic compounds do in water. And the other reactant, sodium bromide, is also aqueous. So when you put this solid compound in water, the action of the water separates the sodiums from the bromides. All right, when we pour the two reactants together, now they're all together in the same beaker, there's a lot of swimming around. Think of these guys as like bumper cars. Okay, and we predicted that the potassium and the bromide would form a new product, and the sodium and the chloride would form the other product. So that was our prediction. Okay, well, here's the deal. Double replacement reactions only they only react if one of two conditions are met. So they only go if on your product side you have formed a precipitate. Precipitate is an insoluble ionic compound. The other condition that could happen is that a molecular compound forms. Okay, that's not going on here. These are both ionic. However, look at this. There are some guidelines that help us figure out which ionic compounds dissolve and which ones do not. Okay, this is going to be important for you to remember. Anytime you have an ionic compound that contains sodium or potassium or ammonium for a cation, or nitrate or acetate or almost any chloride, if your compound contains any of those, then it simply cannot be a precipitate. Compounds with these ions in them always dissolve. So I've got here potassium bromide, but potassium compounds always dissolve. And I predicted sodium chloride, but sodium compounds always dissolve. So what we actually have here in this reaction vessel are a bunch of cations and anions that just have no inclination to come together and form a new compound. This is just a soup with a bunch of cations and anions swimming freely. And what that means is that when you put these two ionic compounds together, there is no reaction. Okay, let's practice with another example. Let's consider the reaction between potassium chloride and silver bromide. All right, so there are my two ionic compounds, and each of them is in solution. So my first step is to predict what the products would be by doing the swapping of the anions. So I'm going to say that I predict potassium will react with bromide. And again, guys, remember to refer to your periodic table. Potassium's +1 and bromide is 1-, so that's the correct formula. And my second predicted product would be the silver cation. Remember, always in your ionic formulas, the cation is written first. Silver with chloride. Silver down here is, you probably can't see that, it's so tiny, but silver is a +1 cation, and my chloride anion is -1. So I'm predicting these for my products, and then I make sure the equation is balanced. This one is. All right, the next step is to consider what's happening on a particle level. Because this AQ is written, I know that potassium chloride is actually in solution. Potassiums and chlorides freely swimming around. They're separated from each other. And the silver bromide, because of this AQ, that is telling me that the silver and the bromide have also been separated from each other in solution. Water does that. Water pulls the cations and anions apart. So these are my two reaction vessels. I'm going to pour them together for the reaction. And now I've got everybody swimming around. And I've predicted that the potassium and the bromide are going to form a product, and the silver and the chloride would form a product. Let's refer to our guidelines. Okay, remember, any compound with potassium in it cannot precipitate. It's not going to be a solid, insoluble ionic compound. Instead, this guy stays dissolved, so separate them out. How about the silver chloride? Well, most chloride compounds do dissolve, but I have these three that don't. These three compounds are precipitates. They are insoluble. So when the silver cation and the chloride anion bump into each other in this soup, boom, they stick. And they form a solid which is actually going to sink to the bottom of the beaker. So let's write what's happening on a particle level. We have the potassium cations separated from the bromide anions, and we have the silver chloride solid. That's your precipitate. Since it is a solid and the action of the water does not pull them apart, we're going to keep that formula written like this. All right, the last thing for us to do is to look at this complete ionic equation and see if there are any species that are exactly the same on both sides of the reaction arrow. Do you see how potassium is an ion as a reactant and as a product? So I'm just going to take that out. And do you see how bromide is an ion on both sides of the equation? So I'm going to take that guy out. And my net ionic equation is going to be chloride anions plus silver cations form this new stuff. This reaction does occur because something new is formed, a precipitate. Okay, let's look at another. So on my third example, let's put potassium carbonate with calcium chloride. There are my two reactants. All right, first step is to predict the products. So I'm going to switch partners with these anions, and I'm going to put potassium with chloride. Do you guys see what I did? In this formula, this potassium carbonate has a 2 here. after the potassium, that just means there are 2 potassium cations in this compound. That doesn't mean there will necessarily be 2 in the new compound. So if you can see my color coding, I color-coded green for potassium, but the 2 just applies to this formula. Okay, so potassium I know is a 1+ cation, and chloride I know is a 1- anion, so they come together in this way to make the formula of potassium chloride. My other predicted product would be the calcium cation and the carbonate anion. Calcium is 2+, and carbonate is a polyatomic ion with a 2- charge. So that's how we write the formula. Those are my predicted products. Step 2, balance the equation. I have 2 potassiums in, but only 1 came out. I need to put a 2 here. 1 carbonate went in, 1 came out. 1 calcium went in, 1 came out. 2 chlorides went in, and my 2 shows me 2 chlorides coming out. All right. Next is to consider what's happening on the particle level. This is an aqueous solution, so what I really have in the beaker is 2 separated potassium cations and the carbonate. So let's show that. Here's a potassium, here's the other potassium, here's the carbonate. Okay, now notice these 2 potassiums don't stay hooked together. Okay, there are 2 of them in the formula unit, but once the water acts on them, it rips all the cations away from the anions and from each other. My second reactant in aqueous solution is the calcium cation and the 2 chloride anions, again, separated from the calcium and separated from each other. All right, let's pour the 2 beakers together so that everybody is swimming around here. I predicted 2 potassium chlorides. Potassium chloride, potassium chloride. But again, any compound that has potassium in it cannot be a precipitate. Potassium compounds always dissolve in water. So this is not happening. Instead, potassiums and chlorides are free to swim around. How about the second predicted product, calcium carbonate? So here's calcium, cation, definitely attracted to carbonate anion. And when I look at my guidelines, is there anything here to tell me that calcium carbonate cannot be a precipitate? The answer is no. Calcium carbonate is also not a molecular compound. It's very much a metal cation and a polyatomic anion. So this is ionic. And because I don't have a guideline telling me that it can't be a precipitate, I'm going to make the assumption that it is a precipitate. Okay, so potassium chloride definitely does not precipitate, but this guy does. So they find each other and they sink down here to the bottom of the beaker. They're out of the soup. Those ions have been pulled out of the solution. These guys are still in there. So let's go back to our complete ionic equation. Potassium chloride, I know is aqueous. So I'm going to say there are 2 potassiums and 2 chlorides. But the calcium carbonate is the precipitate. Calcium carbonate does not dissolve in solution, and I'm going to denote that with an S for solid. That's my complete net ionic equation But more importantly, let's rewrite it as a net ionic equation by looking for the spectator ions. I see 2 potassiums, cations, and 2 potassium cations. So I'm taking them out of there. And I see 2 chloride ions and 2 chloride ions. So I'm going to take those guys out of there. And that means that the pieces that are left, the carbonate anion, the calcium cation, and the calcium carbonate precipitate, that is the net ionic equation. Okay, let's try another. How about a reaction between sodium hydroxide in solution and nitric acid in solution? Okay, 2 compounds in aqueous solution. So my prediction is going to be that the 2 anions will switch places. And I'm predicting that I will form sodium nitrate. Again, as I'm writing this formula, I'm using my resources. Sodium is a +1 cation, and nitrate is one of the polyatomic ions. It has a -1 charge. The other product that I'm predicting would put the hydroxide with the H. So guys, I'm going to write it like this, HOH, which is just kind of a silly way to write water. And next I'm going to balance the equation, which is already balanced. So that's my balanced molecular equation. But now I want to think on the particle level. So I'm going to change this molecular equation into an ionic equation. Sodium hydroxide aqueous tells me that I actually have sodium ions separated from hydroxide anions. Here they are, sodium cation separated from hydroxides. And my second reactant, okay, time out. This is not an ionic compound. It's not made of a metal and a nonmetal or a metal and a poly. It's made of hydrogen nonmetals and nitrogen and oxygen. So remember, guys, this is an acid, recognizable because it starts with H. And furthermore, it's a strong acid. And you remember that strong acids are unique in that in the presence of water, they actually turn into ions. So in a solution of nitric acid, I actually have hydrogen cations and nitrate anions. Okay, pour the 2 reactants together. Everybody's in the beaker now, in the reaction vessel. And I predicted sodium nitrate as a product, and I predicted HOH. Let's think about, oops, can you see that? Let's think about sodium nitrate. The guidelines tell me that any compound containing sodium cannot precipitate. Sodium compounds are always soluble. So if these guys are in water, they are separate from each other. HOH, on the other hand, there is a Coulombic attraction between this hydrogen cation and the hydroxide anion, and when they find each other, boom, HOH, H2O, water. So this double replacement reaction happens not because we formed a precipitate, but because a molecular compound, specifically water, was formed. The formation of water pulled the hydrogen cations and the hydroxide anions out of solution and clumped them together. They're united here. So we have the sodium cations and the nitrate anions separated from each other, but the H and the OH found each other. You can write it H2O. And now, last but not least, let's look for spectator ions and remove them. The sodium cation is exactly the same on both sides, so we're going to take that out. And the nitrate is exactly the same on both sides, so let's take that out. And what we end up with is hydroxide anions plus hydrogen cations form the molecular compound water. That's the net ionic equation. All right, we have one more. Last example. Let's put hydrochloric acid reactant with sodium carbonate, the other reactant, and both of these are in aqueous solution. All right, so remember, in a double replacement, we're going to have the anions switch places. So that means that I'm going to put sodium cation with chloride anion. Again, don't bring the 2 over. This 2 is present because in this compound, there were 2 sodiums. But in a sodium and chloride compound, sodium 1 plus, chloride 1 minus, we write it this way. And then we're predicting that the second product would be between the H and the CO3. Okay, so the hydrogen would be a +1, and carbonate is 2 minus. So this second product would need 2 of the hydrogens to go with that carbonate. Okay. Next, we need to balance the equation. 1 H goes in, but 2 H's came out. 2 chlorides go in, 2 chlorides come out. 2 sodiums go in, 2 sodiums out, and 1 carbonate goes in, 1 carbonate comes out. Okay, there's my balanced molecular equation. Right, now let's go to the ionic equation. HCl, remember, is a strong acid, and strong acids in aqueous solution turn into ions. So what we're actually going to have here are 2 hydrogen atoms, and 2 chlorides. So let's take a look again. Here was the HCl molecule. Here's the other HCl molecule. But once they hit the water, the action of the water pulls this hydrogen off. It becomes a cation, and the chloride becomes an anion. Action of the water creates 2 ions out of a molecular compound. That process is called ionization. Okay, that's our first reactant. And then we have sodium carbonate. So Na2CO3 hits the water. The action of the water pulls the 2 cations away from the anion and away from each other. So this is what's going on with our second reactant, 2 sodiums and a carbonate. All right, now we need to pour the 2 reactants together to see what they do when they're swimming together in the beaker. So remember, we predicted that we would have 2 sodium chlorides. Well, there's one, and there's one. But again, any compound that contains sodium is not going to be a precipitate because all sodium compounds dissolve in water. So this is not happening. Instead, this is. And this is. Let me just switch them around a little. Freely swimming around. Okay, the other product, H2CO3. H2CO3. So guys, that compound is called carbonic acid. See how it starts with H? I want you to remember something really special about carbonic acid. It's really unstable. And almost immediately after it forms, it's going to do some shenanigans. Here's what's going to happen. One of these O's is going to break off, leaving you with not carbonate CO3, but CO2 molecules, and that oxygen that broke off is going to make water. So what we formed here, almost immediately after the carbonic acid formed, was H2O. Again, the H's both bonded with one of these O's, making water, and the CO3 carbonate anion lost its oxygen and became CO2. You've heard of CO2, carbon dioxide. That's a gas. It's a molecular substance and a gas. And so is this a molecular substance? Okay, meanwhile, remember those sodium chlorides stayed in solution. Oops, and there were two of them. So I had the two sodiums and the two chlorides swimming around, but I also formed water and CO2. And guess what? The CO2 gas is going to form bubbles and blah, 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 actually leave the beaker. So as the reaction progresses, what you're going to be left with is sodium and chloride ions in the water. And CO2 is also a product. It just leaves the vessel. So this double replacement reaction was driven by the fact that two molecular compounds formed. We made a gas, CO2, and we made water. All right, last but not least, let's find our spectator ions here. So we have, let's see, we have two chlorides on both sides of the equation. So we're going to take those out. And we have two sodiums on both sides. We're going to take those out. And our net ionic equation this time is two hydrogen ions, two cations, and a carbonate anion forming H2O and CO2. Okay, guys, so as you're working through double replacement reactions, keep these reminders in front of you. Remember, when you're writing new formulas, to always refer to your periodic table for the charges on the cations and the anions. And after you complete the molecular equation and balance it, then go about separating any ionic compounds or strong acids that dissolve in water, and keeping intact any molecules that form or any precipitate ionic compounds that form. Okay, I hope that was helpful.